All right, guys, so the goal of this video is to talk through 8 different multiple choice questions and look at some different concepts and some terminology and just make sure that we're comfortable with everything as we go. All right, so the first thing that we're going to do is we're going to go into this one right here. Let's just get started. So a seawall, as diagrammed, contains 2 apertures, right? So we got 2 holes, one right here with the waves coming through and one right here with the waves coming through. Wavefronts represent crests moving in phase. Which letter represents the maximum displacement above equilibrium? So wavefront is a crest. Okay, now they didn't actually have to say that. That's what we normally assume. So each one of these lines represents a crest. Now remember, the crest is when I have my line, it goes above and under. So this right here is a crest. Okay. And this one down here is a trough. Okay, and it says which one represents maximum displacement. Well, the key here is to recognize that there's 2 waves, right? One, which is the wave which is diffracting, right? This is diffraction. The wave is spreading out as it goes through this hole. Okay, there's a second wave that's right here, which is diffracting out of this hole right here, right? So you've got 2 different holes, therefore creating 2 new waves, and as they cross, that's where we're going to get a maximum, right? So the idea of superposition says that as long as 2 waves are the same type, which these are, and they meet at the same place at the same time, when they meet, we're going to have the vector sum of their displacements. And so in order to get maximum displacement above equilibrium, then I want 2 wave pieces that are above equilibrium, or in other words, I want 2 crests that are crossing together. And you can see that right here at II. So II, there's 3 I's there, is where I have 2 crests that are crossing. Those 2 crests are going to add together to get a wave that is twice as high as it would normally be. All right, next we move on. Which letter represents minimum displacement below equilibrium? Okay, and I'm gonna clarify this. What this means is the minimum value. It really should be still a maximum displacement below equilibrium, but the lowest part of the wave. Okay, and it should make sense that the lowest part of the wave is going to come when 2 troughs cross each other. Okay, so that's this point right here, II, right? That's a trough for the green one. It's also a trough right in the middle of the blue ones, right? The trough should happen halfway between your 2 crests. So therefore, II is going to be a position where the 2 troughs meet up. Okay, and the last question, which letter represents the natural level of the water? Well, where is that going to happen? Well, that's going to happen when a crest and a trough meet at the same time. And so you can see that right here in letter I. It's on the crest for the green, and it's right in the middle of the 2 blues, so it must be the trough there. And a crest and a trough should add together to give 0, or the natural level of the water. All right, awesome. Let's move on. Let's do another one that's similar to that right here. In a shallow pool of water, there are 2 needle-light dippers that move up and down at the same constant frequency. The water waves move outward from each source as shown in the drawing. The wave crests represented by solid lines have an amplitude of 4 centimeters, 0.4 centimeters. What is the displacement of the water relative to the undisturbed water level at the point labeled P? All right, well, it told us that the line is a crest, okay, which has an amplitude of 0.4 centimeters, okay? Now, if the crest is 0.4, so if I have my line here, if the crest has an amplitude of 0.4, then that means that the trough down here should also have an amplitude of 0.4. Now, why is that important? Because P is right in between those 2 gray lines, and it's also right in between the 2 black lines, which means that it's actually going to be 2 troughs that are meeting up. Now, if the first trough was 0.4 centimeters below, and then you have a second one which is 0.4, the principle of superposition says that we just add them together. And so therefore the displacement should be 0.4 twice, which is going to give us an answer of E, right there. All right, now while we're on it, keep that in mind. We're going to go right over here. That was fun. And we're going to do one more. Go ahead, try to answer this one. This should be easy considering the discussions we just had. Pause the video. All right, so hopefully you've had a chance to think about it, recognizing that P is on the crest of both the black and the gray. So if I have two crests, each of 0.4 centimeters, the principle of superposition says we'll add them together where they meet. So therefore the water there must be 0.8 centimeters above equilibrium. Awesome. Hopefully you're going well so far. Let's move on to this guy right here. A tight horizontal rope with one end tied to a vertical wall is shaken with frequency F. So the traveling wave of wavelength is created in the rope. The rope is now shaken with the frequency of 2F, which gives the new wavelength and speed of the wave. All right, well, first off, you should recognize that the medium itself, the rope, is not changing. You're not changing its length, you're not changing its tension, you're not changing anything about that medium, you're just shaking it harder. Now, shaking it harder doesn't actually mean that it's going to move faster. Okay, the wave is going to move at the same speed because the movement of the wave is determined by the particles of the medium itself, right? Just like the speed of sound in air is always the same. Right? It doesn't matter how loud or how quiet or how high or how low the frequency is, it's going to have the same speed no matter what. So here, speed has to be the same. That means it can't be B and it can't be D. Right? The speed still has to be frequency times wavelength, just like it was before. Okay, so it's got to be one of those two. Now, if we look at the other part of the question, that means it's either got to be A or C. Now, without even thinking about it, we know that the answer has to be C. The reason being is that the frequency's been doubled, therefore the wavelength can't stay the same. It couldn't still be A. If we look at it a little bit deeper and we say, well, V has to be the same, and the frequency is now 2 times F, what does the wavelength have to be so that this can still be the same V as before? Well, it's got to be, you got to have the 1/2 to cancel out the 2. So half of the wavelength, which is wavelength over 2. All right. So just putting those ideas together and thinking about different kinds of questions in a slightly different way. All right, let's go ahead and look at something with a pipe, because we can. All right, traveling waves of wavelength 32 centimeters are created in a closed open pipe X. Okay, so right here of length 40 centimeters and an open pipe of length 50 centimeters. In which pipe or pipes will a standing wave be formed? All right, so this is a good question, right? This is now really going to test whether we are able to understand what's going on. Okay, so wavelength of 32 centimeters, all right? So let's think about that. If I have, I got to have a node, right? I'm assuming now that I'm being able to create a standing wave. So if I had a node there, if I went through one full wavelength, so I went up and then down and then back to the middle, right? That would be 32. So how much is left? I have 8 left, okay? In 8, how much of a wave would I go through? Well, in 8, that's 1/4 of a wave. So I would go from the center, right? So I'm thinking of my waves here, right? At this point here, I've just come up, so I'm right there. 1/4 of a wave would be up to the top, right? Like that. That's 1/4, 1/4, 1/4, 1/4, right? So 1/4 of a wave would be from the middle up to the top. Okay, now if I do the same thing here, what do I see? Well, if I go down and up and down, that's my 32. That's one wavelength. Then I'm going to get this right here. Notice how I have the antinode. It's perfect for the antinode, exactly what I wanted. So definitely X. X definitely will give me a standing wave, one that will give me, hopefully, the sound that I'm looking for. All right, let's look at the open pipe. Okay, so the open pipe, remember, at this point has to be open, right? It's got to be an antinode. So if I start there and then go down and then come back up, okay, that is 32, right? That's one wavelength. How much is left? Well, I now have 18 left. Now, what's going to happen in 18? How much of a wave am I going to go through? Well, a wavelength is 32, so half of a wave is 16. So if I go 16, I'm going to go from the top down to the bottom. That's a half, but then I got 2 left, so I'm going to go like this, which is not going to be giving me an antinode on this side, right? If I do it on the other side, it'll look something like this, and it'll go up. There's my half wave, and then I've got 2 left over. Again, it's not going to give me an antinode. It is not going to be a node, but it's not an antinode either, which means I'm not going to get the standing wave that I want. It's not going to be a perfect situation where I get these standing waves. So therefore, the answer is going to be X only. Awesome. We're getting close. Let's try another one. Which diagram correctly shows the wave fronts of a wave entering a medium where it will travel slower? Okay, so it's going to travel slower. Now, what does that mean about the wave if it travels slower? Okay, now remember, when we do this, the frequency has to stay the same. Okay, and we know that the velocity equals frequency times wavelength. Okay, so if the wave is traveling slower, that means V needs to be going down. Since frequency can't change, that means the wavelength has to go down. Okay, which means it can't be A and it can't be D. Both of those show longer wavelengths. Okay, so I need shorter wavelengths, which is what I see in B and C. So now the question is, as the wave comes in, okay, should it bend this way or should it bend that way? Should it be bending towards the normal or should it be bending away from the normal? All right, so hopefully you got the idea that it needs to bend towards the normal. Towards the normal is slower. Away from the normal is faster. All right, so the answer here should be B. All right, let's do another one. Okay. There we go. Ooh, how about this? Unpolarized light of intensity I naught is incident on 2 polarizers, one behind the other with parallel transmission axes. The first polarizer is rotated by 30 degrees clockwise, and the second 30 degrees counterclockwise. What is the intensity transmitted? All right, well, let's consider. So we've got 2 polarizers. At first, they are parallel, right? And then we've got light coming in with I naught. Okay? Now, in the second scenario, we're going to rotate them. So one of them is going to be rotated 30 degrees clockwise. So that's going to be this guy is going to be over this way, 30 degrees. And then this guy is going to be rotated that way 30 degrees, which means it's going to be something like this. All right, we still have the same light coming in. Now, remember, when it goes through the first polarizer is just going to polarize it, which means I'm going to lose half of the light. So this is automatically going to be 1/2 I naught, right? Because this is going to take out anything that is perpendicular to the transmission axis, okay? So perpendicular's all gone. We'll keep the parallel components. Now the light's coming through like this. Now, as it gets to the second one, right? As it gets to the second one, it's been rotated 30 degrees. The other one's been rotated 30 degrees in the other direction, okay? Now, if this one's been rotated 30 this direction, that's been rotated 30 that direction, what does that mean? Well, we have a formula, don't we? So at this point, we use Malus's law, which is that I equals I naught cosine squared of theta. All right, so the I naught for the second polarizer is 1/2 of the original, okay? And then I want cosine squared of theta. Now my theta here is going to be 60, so I need to be able to do cosine of 60. Now you can use your calculator, or if you've done this in math, you can make your 60-degree angle. You can do 1 square root of 3 and 2, right? And then you can do cosine is adjacent over hypotenuse, which would be 1/2. So it would be 1/2 squared. So 1/2 squared is 1/4 times another 1/2 would be 1/8. And so it's I naught times 1/8, which is letter C. Woohoo! We got that one too. All right, let's see. Oh, we got one more. Woo, yeah, that's good. I wasn't ready to be done yet. Here we go. Last one. Which of the following does not apply to longitudinal waves? Pause it and think about it, and then come right back. All right, so hopefully you got polarization. Superposition. We know superposition works because we can add different amplitudes together. It doesn't matter whether the particles are moving up and down or side to side. A good example of this is if you've ever listened to two speakers going at the same time. If you listen in exactly the right place, sometimes it's louder and sometimes it's softer. If you haven't heard this yet, just hang on. We'll do it. We'll do it in class. I promise. We'll take a chance, take a situation where we hear this, and you'll hear that with sound waves. And remember, sound is a longitudinal wave. We will be able to hear the louder and softer positions. Now, superposition and interference are basically the same thing. And so if superposition is allowed, so is interference. Now, letter B is the formation of standing waves. We know standing waves occur inside a pipe, right? Or on a string. String is not important because the string is transverse, but inside a pipe, when we're making sound, right? Sound is longitudinal, and because we can form a standing wave inside of a pipe, like with an organ or a pitch pipe or something like that, then we know it must work for longitudinal waves. Therefore, the only answer is polarization. And of course, the reason is that when you have a polarizing lens, it polarizes vertically or horizontally or whatever other direction, but the particles in a transverse way, or so longitudinal wave, are moving to the left and right. And so they're all just going to be able to go straight through there. Nothing's going to be absorbed because there is no up and down, right? Remember when we talked about this before, we said, well, it's kind of like a fence, right? Maybe you have some type of wave, right, that is going through there, right? And if the wave is going through, if I'm shaking the string up and down, it goes through there no problem. If I shake the string side to side, then the wave's going to be running into the sides and it won't make it through. Well, what if I were shaking it forward and backwards, trying to throw balls straight through and back? Well, that would work, right? I could be able to throw it, a single ball forwards and backwards through the lens with no problem. So that's kind of the idea that we're looking at. It doesn't affect, it won't be polarized. There's no way to polarize a longitudinal wave. All right, and showing you, we just finished all of them. So that's it. Next video.